Thank you for the introduction, and thank you everyone for coming, especially during this tough time. I'm Yuxiong from CMU. It is a great pleasure to be virtually here and talk about my work on learning to learn more with less. Okay, let's start with a silly image. Some of you have probably seen this object before, but I guess for most of you, this is the first time. This object is called powder pot. Now let's find the powder pot in this image. Although I cannot see, I'm pretty sure that many of you quickly give the right answer, even though these two powder pots are in different poses and viewpoints. You see, remarkably, we humans are able to recognize a never before seen object from even a single image. How if we want machines to recognize this novel object powder pot? That is, taking an image of a powder pot, machines automatically understand its semantic label. To achieve this, the current paradigm is based on supervised machine learning. In this paradigm, we have a model, which is a primary choice function that maps from images to target labels. The most successful models so far are deep learning models, which are a composition of many nonlinear functions. To learn the model, we show examples of image and target label pairs. Of course, here the target labels are defined by humans. With the model, this image should be labeled as powder pot. Humans have already labeled it as powder pot. We show another powder pot, another powder pot, and another powder pot. We have to show at least thousands of photos of like this in order to get the model to recognize the pattern of the powder pot. Recall that you guys only need a single image. You may think that this is not a big deal, since we are in the big data world. Why don't we just simply collect more data? Unfortunately, this is not the case. We are actually living in a long-tail distributed world. In this world, a few classes like cats are common in the hand of the distribution with large amounts of data, while many classes like this loris species are rare in the tail of the distribution with limited data. Simply collecting data doesn't scale, since we have to recollect huge data for each new class. Also, human annotation is expensive and sometimes requires expertise. In practice, it becomes even difficult to collect and annotate data for rare concepts and events. For example, while being able to recognize a child chasing a ball is critical for self-driving cars, I believe that no one is willing to actually put a child on the road to get the design data. So there is really no way to get around this fundamental lack of data issue. How could we build more powerful learning machines that are able to recognize a rare or novel class, such as loris, from one or only few annotated examples? This few-shot learning problem is the focus of my talk today. More formally, in few-shot learning, such as few-shot loris classification, we are given only a few training examples of loris, and we aim to learn an accurate loris classification model. Here, shot means the number of training examples, and for example, in one-shot loris classification, we have only a single training example of loris. Well, while we have only a single example for this novel class loris, we have many common or base classes with large amounts of labeled examples. For example, we have lots of cats, dogs, and fishes. So we address a large collection of few-shot classification tasks of base classes. We address the few-shot cat classification, few-shot dog classification, few-shot fish classification, and so on. By doing so, we learn how to learn an accurate cat, dog, or fish classification model from few examples and obtain certain shared experience or skill that is useful for addressing few-shot learning in general. We then use this prior experience to guide the model learning for the loris class. Now, we are not learning purely from data, but learning from experience. We call our work a form of meta learning or learning to learn. More precisely, I have proposed the principle of meta-learning framework that allow us to address a rich space of few-shot learning tasks in a unified way. While existing work largely considers few-shot classification, my work also addresses how to localize, detect, and segment novel objects, and recognize their actions from few videos. In addition to discriminative recognition tasks, I consider how to synthesize objects in novel viewpoints and poses from the single image, and even reconstruct their 3D shapes. Not only for single objects, but I also want to detect the uncommon object and object interaction, and even enable robots to interact with objects and humans in a dynamic few-shot environment. More broadly, few-shot learning is not limited to visual domains, but exists in a variety of modalities and their intersections, such as in visual question answering that uses both images and natural language questions, and recognition in 3D light-up points cloud. While my work has focused on using computer vision and robotics tasks as illustrative applications, the underlying mechanism is general and applicable to other fields, including natural language processing and reinforcement learning. In this talk, I will focus on several representative tasks: few-shot classification, detection, and interaction. In addition, this is a flexible framework that allows us to integrate various types of experience and knowledge. For example, I have investigated how to learn generalizable feature representations through unsupervised learning and compositional learning, how to grow a model architecture through developmental learning, and how to interact with the environment through predictive learning. In particular, I have explored two types of experience that are especially useful for addressing few-shot learning: learning to generate data and learning to transform a model. These two classes of insights are the focus of my talk. In the first half of the talk, I will show how to address few-shot classification in different ways, from a new perspective of learning to generate data that are most useful for learning classification models. And in the second half of the talk, I will focus on a more radical idea of learning to transform model and show that it is consistent and effective for different tasks. At the end of the talk, based on these two bodies of work, I will discuss more formally our proposed meta-learning framework. Now, let's start with the first insight of learning to generate data. When we have limited data, a natural way is to generate additional data. But the question is, given a single example of this novel class Loris, why do we expect that it is possible to generate additional data? Well, the visual world is highly structured, and rich modes of intra-class variation, such as camera poses and lighting conditions, are shared across classes. For example, in the base classes, we have cats in different poses, like cats sitting and cats climbing trees. Such knowledge of the shared modes of intra-class variation, if learned on the base classes, may allow the machine recognition system to hallucinate what Loris might look like in other poses, like Loris climbing trees. These hallucinated examples could then be used as additional training data to build better classifiers. Unfortunately, building models that can perform such hallucinations is difficult. There has been significant progress in synthesizing visually very realistic images by using approaches like generative adversarial network scans. Look how realistic these synthesized images are. But recent work shows that these images are still not that useful for recognition tasks, since they are not optimized for learning classifiers. Our key insight then is, instead of optimizing visual realism, we should aim to generate data that are directly useful for learning classifiers. Such generation can be performed effectively in a feature space rather than going down to the level of raw images. So we first train a standard convolutional network on the base classes as a feature extractor. Now, let's see how we perform data generation in this feature space to address a few-shot classification task on novel classes. As an example, here we show a 4-way classification task that classifies 4 novel classes, including Loris, with a few training images per class. We first use a trained convolutional network to extract their features and construct the corresponding small training set S-train. We now introduce the generator G to produce some additional examples for each class. The generator G is a neural network. By sampling a city example from S-train and sampling noise vector Z and passing them to the generator G, we obtain a generator example. We treat its label the same as a city example. We perform such generation for all the 4 classes and obtain a set of generator examples. Combining these generator examples with the original S-train, we now create an augmented training set. This augmented training set is used to learn the classifier H. The question then is, how can we learn good generator G to facilitate the learning of the classifier H? We achieve this by first leveraging the mental learning process. Through mental learning, we simulate a large collection of few-shot classification tasks from the base classes. Here, each row is one of the constructed 4-way classification tasks by sampling 4 random base classes. Each task consists of all small training set and held-out validation query set. The training and query set are constructed by randomly sampling few images from each of these 4 classes. We now learn the generator over these constructed few-shot base classification tasks. Consistent with the process before, we perform generation in the pre-trained feature space. For the first base task, given the small training set S-train, we initialize the generator G to generate additional examples and produce an augmented training set. This augmented training set is then fed into the classifier H to produce the final loss on the held-out query images. We backpropagate the gradients of the final loss and update not only the parameters of classifier H, but also the parameters of generator G. By jointly optimizing both the generator and the classifier, our generator is trained to produce the kinds of examples that are directly useful for class distinctions. We then sample another base task, perform the same training process, and continue updating the parameters of generator G. Note that here we have a single generator G that is shared across different tasks. We repeat such training process over and over again on a variety of few-shot classification tasks and obtain generic category shared generator G. We then use this learn generator G to augment data for new classification tasks on novel classes. So here, there are 2 keys to generate data that are useful for recognition tasks. First, end-to-end training of the generator and the classifier, so that the training of the generator is guided directly by the recognition task objective. And the generator and the classifier cooperate with each other to boost the recognition performance. Second, mental learning over a large collection of few-shot classification tasks, which makes the learn generator shared across different tasks and can be used to address novel classification tasks. Note that here, significantly different from GANs, we didn't use any realism objective. So our generated examples might not look pretty, but they are useful, as demonstrated on the large-scale ImageNet-based few-shot classification benchmark. The benchmark has 389 base classes for learning the feature extractor and the generator. We evaluate the performance on 311-way classification of novel classes. We compare mental learners without and with generator. We look at state of our prototypical networks Pn and matching networks Mn, which can be viewed as different types of classifier H. We can see that our generation strategy significantly improves novel class accuracy by up to 6 points for Pn and 2 points for Mn in the challenging one-shot learning case. This shows that our approach is general and can work with different mental learners. I have shown that simple end-to-end learning is able to train the generator to produce examples that are useful for classification. But a natural source of supervision is missing here, which is also significantly overlooked by other existing mental learning work. Recall that for base classes, we actually have a large amount of real examples. From these examples, we can pre-train strong classifier H star. We will show how we leverage such information to further guide the training of the generator on base classes. Ideally, the hope is that the classifier H trained on the augmented set with the generated examples should be as close as possible to the classifier H star. Motivated by this observation, we introduce a large sample classifier H star into the previous generation framework and use it as additional teacher to guide the training of the classifier H and the generator G on the base classes. Now, our goal is to minimize the difference between the classifier H and the teacher classifier H star. To this end, we minimize the difference of the predictions P between H and H star on the head-out query examples. We achieve this by introducing a knowledge distillation loss function, and we back probability gradients to update both the parameter of the classifier H and the generator G. By doing so, our generator is trained to produce the kinds of examples that enable the classifier H to make predictions similar to the desired large sample teacher classifier H star. For new classification tasks on novel classes, similar as before, we directly use this learn generator G to augment the small training set. Note that for novel classes, we don't have a large sample set, and we don't have any teacher classifier. The comparison on the previous ImageNet benchmark shows that by leveraging additional large sample teacher classifiers to train the generator on base classes, the few-shot performance on novel classes significantly and consistently improves. To analyze the effect of the generated examples, we visualize their feature vectors by projecting to 2D space using t-SNE. Here, the cross shapes represent the real examples of 5 novel classes. The star shapes represent the city examples, which are the input to the generator. And the triangle shapes represent the generated examples. Also, we show the images corresponding to the feature vectors. Here, the city image of the novel class. Since our generator produces examples in a feature space, it is difficult to visualize them as images. So we visualize the generated examples by using their nearest neighbor real images in the feature space. We can see that we are able to generate diverse examples which are significantly different from the city example. More interestingly, due to the discriminative training of the generator, our generated examples tend to cluster around class boundaries. This explains our generation, why our generation is useful for learning classifiers. Because the generated examples directly contribute to formulating classifier decision boundaries. Until now, we are generating data in a feature space. It would be interesting to move a step further to generate data in image space. This is interesting because we are doing computer vision and we love images. And more importantly, when we generate data at image levels, we could learn better feature representation that is suitable for both generated and real examples. This provides more flexibility to the entire learning system and could potentially further improve the recognition performance. While directly generating pixels is a challenge, modifying an existing image to be a new image would be something feasible. A simple approach is to compose two existing images. For example, given a single image of this novel class Loris, we could find a similar image from the base classes. We then combine these two images to generate a new image. How could we compose these two images in a meaningful way? Ideally, we want to approach that to compose foreground and background objects in a semantic way to generate realistic images. But this requires strong semantic supervision, and here we don't have such information. So I'm taking pieces of real images and learning how to compose them. Specifically, to maintain local image structures, we divide the images into n by n patches, and here is an illustration of 3 by 3 patches. Now, our generator learns the combination weights. We then generate the composed image as a weighted average of these two images. How do the composed images look like? Here are some examples. The first rows are the images of novel classes. The second rows are selected images of base classes. We can see that our approach learns to find examples that are similar in shape and geometry or similar in appearance, depending on the specific novel classes. The third rows are the composed images. For example, to recognize vase, the geometry shape is more important, the specific texture is less crucial. So our approach finds the trash can and copies the texture to vase. These generated images are not pretty at all, but they seem like hard on the boundary examples that might contribute to formulating classified decision boundaries. Are they useful for recognition tasks? Yes, they do, as evaluated on the previous ImageNet benchmark. And more importantly, by generating images rather than feature vectors, we provide more flexibility to the entire learning system, so the performance on the novel classes further improves and outperforms our previous generation in feature space. As a mini summary, in this body of work, I showed how I address few-shot learning at the data level by learning to generate data. Different from existing approaches like GANs that generate realistic images, I provided new insight to generate data that are close to the class of boundaries, and so they are directly useful for recognition tasks. I showed how I generate useful data first in feature space and then in more challenging image space with consistent performance improvements. I achieved this by combining generative models and discriminating models in an end-to-end cooperative learning way. Now, let's take a more radical idea. Is it possible to address few-shot learning without explicitly generating data? Let's explore more abstract model level by learning to transform model. Again, we aim to learn a low-risk classification model theta from few images. Here's a model consists of a bunch of parameter numbers, which is represented as a vector, and we call it theta. The model theta can be viewed as a decision boundary or hypersurface that separates positive and negative low-risk examples. It is not necessary to be linear, and here for illustration, we visualize it as a line. Similar as before, ideally, what we want is a classification model theta star that will be learned from a large amount of low-risk images. An interesting question then is it possible to estimate theta star based on theta? To answer this question, let's look at the relationship between these two types of models. Again, in a feature space, the model that is a low-risk classifier is a decision boundary or hypersurface. Equivalent, we can say that the classifier is a point in the model parameter space. Few training examples point to an initial boundary theta. When gradually introducing additional examples, the initial boundary is progressively subject to a series of transformation T until it changes to the underlying large sample model theta star. Our main hypothesis then is there exists a generic nonlinear transformation T from few-shot models to the underlying large sample models for a variety of classes. If somehow we have learned the model transformation on the base classes, we could then use it to transform the initial few-shot low-risk classifier to improve its performance. But wait, why do we expect that there is a class-shared model transformation? Intuitively, this transformation captures intra-class variation in a discriminative way and represents how sparse samples change to a category cluster. In our previous data generation work, I showed that the visual world is highly structured, and the shared modes of intra-class variation allow us to generate additional data for novel classes. But now, instead of explicitly generating data, we predict their impact on the learned model parameters. Here we focus on the transformation from specific few k-shot models like one-shot models to the large sample models. But if we look from a fine-grained scale, the transformation T is not a single one-step transformation. It consists of a series of transformations that represent how few k-shot models theta k start from the one-shot model theta 1, pass through theta 2, theta 4, and gradually change to the underlying large sample model theta star. T thus captures the notion of model evolution that predicts how model parameters are likely to change as more training data is gradually ended. Again, if we have learned the model evolution pattern on base classes, we can then hallucinate the model evolution trajectory of novel loris from the initial one-shot loris model. By leveraging such model evolution over different k-shot models, we are able to address a more challenging task of learning classifiers on a long-tail dataset with thousands of cat images, but there's only a single image of loris. Few-shot learning can be viewed as a problem of this more general realistic long-tail recognition. The challenge now becomes threefold. First, we need to learn accurate few-shot models for the tail or novel classes. Second, we need to learn without forgetting and maintain good performance on the hand or base classes. Third, in the setting of few-shot learning, we assume that each class has the same small number of training examples. But here, we need to address a significantly imbalanced distribution. Different classes have a significantly varying number of training examples. I will now show that we are able to address these challenges in a principled way by leveraging the knowledge of model evolution from base classes to novel classes. To this end, we introduce a meta-level network that is specifically trained to regress from few-shot model parameter theta to large sample model parameter theta star. We call it a model regression network T with its own parameters W. Here, our objective function first consists of a regression loss that encourages the transformed model T theta to be close to the desired theta star. We also introduce a performance loss, which is a standard classification loss and ensure that the transformed model maintains a high classification accuracy on the given data. The final loss is the average over all the base classes and minimized with respect to W. How do we design the regression network? Let's look more closely at the property of the transformation. First, it is sample size or shot dependent. For a specific few k-shot model, we have its own transformation Tk to the underlying large sample model theta star. This indicates that we have a series of transformations, each tuned for a specific k-shot model. Second, identity regularization. The transformation is close to the identity mapping for large K. Third, we're actually more interested in estimating the change of model parameters delta theta rather than their absolute values. Based on these observations, we designed the regression network as a single chain residual network. The network takes a different few k-shot model parameter theta as multiple inputs and regress them to large sample model parameter theta star as output. Each of these is a residual block. A subnetwork represents the transformation from k-shot theta to theta star. And the skip connections ensure the identity regularization and learn the delta theta. Also, inspired by the general observation that recognition performance improves on a logarithm scale as the number of training examples increases, we discretize the residual blocks accordingly to be tuned for one-shot, two-shot, four-shot regression, and so on. A nice property is that by construction, this network can be trained in a recursive manner from back to front. So we begin with the last residual block and learn the transformation from 2 power n minus 1 shot theta to theta star. This is easy to learn because it is similar to an identity mapping. Given the learned parameters of this residual last block, we then train the next to last block, and so on, until the one-shot regression. This is also easy to learn because other subsequent blocks have already been trained. Essentially, we leverage the shared regularity between models of different sample sizes. We train the meta network on hand or base classes. For tail novel classes, we take their initial model parameters as inputs to different residual blocks according to their number of training examples. For example, if a novel class has one example, we obtain its initial one-shot model, input here, and get the transform model. And if a novel class has two examples, we obtain its initial two-shot model, input here, and get the transformed model. We now evaluate our approach for scene classification on the long-tailed sum dataset. We use a pre-trained ResNet scene as a feature extractor and learn the model transformation of the last layer. Here's the result of plain baseline that fine-tunes on the target data following standard practice. We also compare with three state-of-the-art approaches that are widely used to address imbalanced distribution. The balanced data baselines include oversampling and undersampling. Oversampling generates redundant examples for the tail classes, and undersampling reduces the number of examples for the hand classes. The balanced loss baseline introduces additional weights in the loss function for each class. We can see that our approach significantly outperforms all the baselines by benefiting from the generic model transformation learned from the hand classes. This figure further details the per class accuracy improvement. The x-axis is a sorted class index. The yellow curve shows the long tail distribution. And here are the tail classes with limited data, and here are the hand classes with large amounts of the data. We now look at the accuracy improvement relative to the plain baseline. Ideally, what we expect for a good approach is that it improves the performance of tail classes while remaining accurate on the hand classes. This is exactly what we have achieved in our approach. We can say that we significantly improve the tail performance while remaining high accuracy on the base. By contrast, the state-of-the-art oversampling baseline doesn't show consistent improvement for the tail classes, and even worse, it hurts the base performance. I have shown that model transformation exists in modern classification models and can be leveraged to address few-shot classification. It is interesting to explore further to investigate if similar model transformations exist in other types of more complex models, and if they are useful for addressing more challenging tasks. In practice, often we are interested in not only classification, but also few-shot detection, which learns an object detector with only a few annotated bounding box examples. Compared with the few-shot classification, few-shot detection is a significantly more challenging and less explored problem. From limited data, we need to both classify and localize multiple objects within an image, as well as dealing with the distracting background regions. Ideally, we would like to simultaneously address few-shot classification and few-shot localization in a unified way. Conceptually, our model transformation work provides such a solution since it reasons on an abstract model level, which might apply to both classification parameters and localization parameters. We show that this is the case for modern scene-based detectors, such as fast RSN. And we learn the desired model transformation on base classes with large amounts of annotated bounding box examples to guide the detector learning for novel classes. We now evaluate one-shot detection on the Pascal dataset. We learn the model transformation on 15 base classes and evaluate on 5 novel classes. Our detector is a standard fast RSN. Here is the result which fine-tunes fast RSN on the novel classes after learning the large sample detector on the base classes. While fast RSN has achieved impressive performance with large amounts of examples, its performance significantly decreased in the few-shot scenario, only 10% MAP. By contrast, our approach doubles the few-shot detection performance and outperforms the recent few-shot detection approach. Also, our approach is general and shows consistent improvement for another type of detector, ULO. In another release setting, we evaluate more challenging long-tail detection on the iNaturalist dataset. This is a really difficult problem, since we need to detect thousands of fine-grained species. Similar as before, the per-class accuracy show that our approach significantly improves the detection on the tail while remaining accurate on the head. We now move forward to investigate the use of our model transformation for an even challenging and difficult type of task, few-shot prediction. This few-shot prediction problem is an underexplored few-shot learning task, but it's critical to seamless human-robot interaction and collaboration. Imagine we have a robot, which is deployed in a natural environment. Now a person performs certain never-before-seen action like greeting. The robot is supposed to predict the future motion of the person after seeing only a few examples, so that it can more effectively interact and collaborate with the person. Here we focus on predicting 3D human pose motion. I will show that we can leverage a similar model transformation to learn motion predictors for novel actions with a few training sequences. To this end, we evaluate a few-shot prediction on the human 3.6M dataset. We learn the model transformation on 11 base actions with thousands of training sequences and evaluate on 4 actions, including eating, with a few training sequences. We predict the future motion in 8 milliseconds. We evaluate performance change with respect to the number of training sequences for novel classes. The y-axis is the mean angle prediction error. The smaller the better. The blue fine-tuning baseline first learns a single predictor for the base actions, and then fine-tunes to be an action-specific predictor for each of the 4 novel actions. The white line shows the oracle performance, which trains the novel predictor with thousands of sequences. We can say that our approach consistently outperforms fine-tuning, and importantly, with only 100 sequences, it achieves the performance closer to oracle, which trained on thousands of sequences. As a mini summary, in this body of work, I introduce a more exploration approach that is able to address a variety of few-shot learning tasks in a consistent manner, from recognition to prediction, by learning to transform models. These interesting results empirically show that there exist rich and useful structures in model space. Inspired by my work, recently some follow-up shows that such structures are beyond few-shot learning and could facilitate other tasks, such as weakly supervised instance segmentation, novel concept composition, and sketch-to-real transformation. From these 2 bodies of work, learning to generate data and learning to transform model, we can see how our proposed principal mental learning framework addresses few-shot learning. Again, we aim to learn Laurie's model theta from few examples. Our goal is that the few-shot model theta should be as close as possible to the desired large sample Laurie's model theta star. Note that we don't have this many Laurie's examples, and we don't have the underlying large sample Laurie's model. To this end, our mental learning framework leverages a large collection of base classes with many examples, such as lots of cats and dogs. From these many cat examples, we could obtain the corresponding large sample cat model. This allows us to learn how to learn a cat model from few examples that approximate the large sample cat model. We show 2 ways to achieve this. One way is to introduce a generative model that generates additional useful data. The other way is to introduce a model regression network that explicitly transforms the few-shot model to be close to the large sample model. We perform such a learning process over a large collection of tasks on base classes and obtain shared experience or skill to guide the model learning for the data pool Laurie's class, so that the few-shot Laurie's model approximates the desired large sample Laurie's model. So as we can show that this framework allows us to leverage various types of experience to address rich space of few-shot learning tasks. Moving forward, my long-term goal is to develop embodied robots in the wild that are able to operate in dynamic and uncertain environment, actively learn from ever-changing data streams and tasks, and make intelligent decisions based on limited information. My mental learning research so far has addressed a set of core component capability towards such agents. I will work on extending this meta-learning vision to deal with data of different modalities beyond RGB images. As a first step, in the context of self-driving cars, I'm working on 3D LiDAR points cloud. For example, I'm addressing LiDAR-based 3D object detection by learning to generate additional data. Compared with my previous work on data generation in image domain, now more explicit domain knowledge, such as a physical constraint, significantly facilitates the generation process. In addition, I'm addressing the intersection between LiDAR data and RGB data. Using the high-resolution RGB image as a guidance, I aim to upsample and complete the low-resolution sparse LiDAR image to be a high-resolution LiDAR image. This is important for the application of self-driving cars because it provides more accurate depth information. Such experience of dealing with different modalities will help develop embodied robots that interact with the physical world. For example, a robot navigates in real-world environment. Instead of passive learning from curated dataset, the robot actively collects desired data in a sample-efficient way using a variety of sensors, including cameras, LiDARs, microphones, and touch sensors. Learning that happens in an online streaming and lifelong manner. Beyond the different modalities, I will also work on extending my mental learning vision to address a broader range of complex real-world tasks. Our current AI agents are specialists, while humans are remarkable generalists. I believe that the mental learning ability not only deals with the lack of data issue, but also allows the machines to have more general capability. Inspired by this, I'm interested in extending my generative models to be applicable to multiple tasks, such as object recognition, 3D reconstruction, and visual question answering. This is in a similar spirit as existing work that learns the general feature representation for multiple tasks, but here I'm pushing forward to the data aspect. As ongoing work, I show that we are able to generate images that are useful for two tasks, view synthesis and object recognition. In addition, I draw an analogy between my end-to-end data generation framework and the model-based reinforcement learning. In model-based reinforcement learning, a dynamics model can be viewed as our generator, and the policy network can be viewed as our classifier. Normally, these two are learned separately. This analogy inspires our current work on end-to-end model learning for policy optimization. So far, I talked about how to learn more with less, and in particular with less data. From a broader perspective, AI systems should be able to learn under boundary resources, not only with less data, but also with less time, less computation, less energy, and so on. This concept of boundary rationality is actually an important aspect of human intelligence and artificial intelligence, as initiated by Herbert Simon. I'm starting to look at such a problem for learning with less time in the context of streaming perception for self-driving cars. As shown in this video, latency is inevitable in a real-world perception system. By the time the system finishes processing a particular image frame, the surrounding world has already changed. So there is a mismatch between the prediction and the current status of the world. To help explore visual perception in this streaming context, I introduced a meta benchmark that folds latency into accuracy. This video shows that the object detection and segmentation results in such streaming setting. We can see that the streaming performance drops significantly compared to the offline setting, and our solution recovers almost half of the performance drop. The key of our solution is that in such settings, the perception should be predictive, and tracking and forecasting naturally emerge as subtasks. As mentioned before, the lack of data issue remains a universal challenge in nearly every field of machine learning and data science, not only for computer vision, but also for other applications such as natural language processing, reinforcement learning, computational biology, healthcare, sensor networks, and wireless system. Building upon my work, I'm also excited to collaborate with faculty and researchers to address few-shot learning in this broader range of fields and disciplines. As a concluding remark, few-shot learning is a fundamental problem of great promise. There are a lot of exciting problems worth working on in this direction, And also, the visual world is highly structured, not only in the well-explored feature space, but also in the less explored data and model spaces. These structures can be acquired by our mental learning framework and are potentially useful for other tasks as well. With that, I would like to thank my co-authors, collaborators, and advisors. Thank you for your attention, and I will take more questions.